Okay, so we're doing a Findabs tutorial. Findabs is for finding absorption systems in a spectrum. Key thing is that it understands UVES Poplar output spectra.
Yep.
So it's got a FITS file there from UVES Poplar. Actually, don't use it on the command line, just run Findabs. It'll ask you for the data file. Helpfully, it doesn't prompt you for a FITS file, but a DAT file. If you pass it a UVES Poplar FITS file, it'll understand it.
Can you pass it a DAT file as well? Or instead?
You can pass it a DAT file, but if it expects wavelength and normalized flux in that case, and then a separate file for the sigma. So wavelength versus sigma. However, it's possible, I can't remember, that if you pass it a wavelength with a flux and sigma column, it will actually understand that as containing both.
Okay.
So you need the emission redshift of this quasar, which is, okay, so we've helpfully determined that the redshift is 2.223. You don't need to put a D0 there, but that's just a force of habit for me with Fortran to make sure that it absolutely understands that that's a double precision number, but don't worry about it. Now, the idea behind Findabs is that it looks for a series of pairs of lines. Some of them are doublets, like in this case the very weak sodium 13303 doublet, things like the magnesium 2 2796 2803 doublet. These doublets are defined in a file. We can maybe look for that later. And then that file has another part to it, which is a list of all the different transitions we want to actually identify once we've found an absorption system. So the first part of Findabs, the first phase, I guess you might call it, is that it looks for absorption systems by identifying a predetermined list of pairs of transitions, or actually more accurately asking you to identify those pairs of transitions. So I'm not going to look for this very weak sodium line because I know it's very weak and it's very rare to find it except for in extremely strong low redshift systems. So I'm going to press no. But I will look for silicon 4 systems, but I'm not going to look for them in the Lyman alpha forest. Now that's why we gave it the emission redshift, so that the spectrum knows where the Lyman alpha forest starts and ends. Obviously looking for absorption systems in the Lyman alpha forest is quite difficult because it's a very confusing area, so I'm just not going to do that in this case, in this example. Okay, hopefully it will bring up an X server when I press that. There we are. Okay, now we can move this box, and what you see here is the what it thinks could be a silicon 4 line, the strongest member of the doublet, the first member of the list in the list of pairs. In this case, is the stronger silicon 4 1393 doublet line, whereas the weaker one, which has half its strength, half the oscillator strength, is up the top. So clearly this is not a pair. This is not a real absorption system. The velocity structure up the top is much different to the velocity structure down the bottom. But that's essentially what it's doing, is just looking for a place at this dashed line where the absorption deviates from 1 downwards, indicating absorption, and then it sees whether it also sees absorption, assuming that it's a silicon 4 doublet at the silicon 4 1402 feature. In this case it does, but it's clearly a false positive. So now to advance, to start it doing the search again further along the spectrum, I'm going to start the search at this red line by pressing the left button.
Mouse.
And so you see it's found the next place in the spectrum then where it finds a deviation from 1 here and a similar deviation over here. It's not using any intelligent ideas about the oscillator strengths or anything of the transitions. It's just looking for deviations from 1 which are coincident according to the spacing of this doublet. So all we do is we keep flicking through until we find a case where we see a compelling match in terms of velocity structure, or somewhere where we otherwise think there is good evidence for an absorption system. So it's not really finding the absorption systems for us, it's just finding places where there could be absorbers and wear the filter in getting rid of the false positives. So everything so far has been a false positive. So far we've not found an absorption system. I'm keeping an eye here on the redshift on the base here, telling me that so far I'm not up to the emission redshift of the quasar. I soon will be. Clearly there can't be absorption systems well above the emission redshift of the quasar. There's a lot of absorption here. It's hard to know whether I'm seeing a real absorption system. What I'm looking for is similar velocity structure. Now maybe that's an absorption system, probably not. It could be an absorption system that's blended with a much more extended one, but I'm not going to worry about that in this case. If I was suspicious that this might be an absorber, I might save it for later and investigate other transitions that might fall at the same redshift later. So far though, no silicon 4 absorbers. That's not one. Given that silicon 4 is a fairly common absorber, it's a little bit surprising that we haven't found anything so far. But once we're starting to get up towards the redshift of the quasar, often you have a silicon 4 forest, and indeed this may be one indication of an absorption system here. Not exactly the same velocity structure, however there's this extra absorption here that might have velocity components out in this area here, which then lead us to think that we may not be seeing the same structure. However, in this case the stronger line in the silicon 1393 is then about halved in terms of the strength of the line in the 1402. So I'm going to select this as a possible absorption redshift. That doesn't mean that I'm sure, it just means that I'm suspicious that that's the case. So I'm going to put the right button now, and normally my habit is to put that at the to select the redshift of the absorber is to just line up on the strongest feature. So by clicking the right hand button there, it selects that and saves that redshift for later, and later on we'll investigate whether we see other absorption lines at the same redshift. So I've now passed the redshift of the quasar, and I sort of think, well, I'm very unlikely now to find any, say, infalling absorption systems infalling into the quasar that might be redshifted with respect to the quasar, so I'm just going to press Q for quit. And you see that it now asks me whether I want to look for carbon 4 doublets. So I'll look for carbon 4 doublets, but not in the laminar for forest. And again, we see the two members of the doublet is so much closer together, 1548 and 1550. Same deal though, one is half the strength of the other, and we're just going to move along the wavelength axis trying to find coincidences. And now we see we've got a very weak carbon 4 feature here that I'm just going to select as being at that redshift there. Moving along, we now see a very strong one. This is probably not the best transition to use because it's heavily saturated. We don't know where the strongest component is, but it doesn't really matter. We can sort that out later on. Just going to select that as the redshift.
If you accidentally go too far, can you go back?
Yeah, it's a good question. If you want to go back, it's not really possible unless there's another place on this side of the on this left-hand side of the dashed line, as to whether there's another place where there's a 5 sigma deviation in both panels.
Okay.
So unfortunately I haven't really coded going backwards in this section. Of course, if you miss it, you can always find another set of transitions, hopefully, that will allow you to find the same absorbing redshift. However, if I do make mistakes like that, I usually just keep a notepad next to me, which I just scribble down rough redshifts that I've missed, and I can go back later on and find those. It was never supposed to be even as ornate as it is now. So here is another absorption system, fairly well defined one. This is another one here. You can see similar velocity structures. Obviously this is a very complicated one. I might even advance this along a bit further just to see if there's any stronger absorption out in this area, but there isn't. So I'll just select this. This could be part of that same absorption redshift. I didn't take a note mentally of the redshift in my mind. So when you've selected a redshift as being a real absorption redshift, it'll then skip ahead a certain number of kilometers per second before starting the search again. So in this case, it might be just a very, very highly extended velocity structure, in which case there might just be one absorption system here, which is just very complex. I'm going to select this anyway. I think that first explanation is probably right. An even more complicated part of it, this is quite something. And again, even more absorption, same sort of velocity structure, so we're probably overdoing it here in terms of selecting absorption. And we may, for example, select that, but there's probably really just one absorption redshift there. It's one very complex system at high redshift. That's a weak one, and I'm just going to skip the rest, so I'm just going to press Q. Now the aim, it depends what your aim here is as to what you're trying to find. If you're trying to find every single absorption system, because you want to know absolutely for sure that you've got everything, and that's really critical, then you can look for all the different pairs of lines that are in this list, this master list that I'll show you soon. So for example, here is a pair of transitions that's common in damp Lyman alpha systems, the silicon and iron combination.
Why did you stop the carbon-4 there? Just for sake of time?
Just for the sake of time and demonstration. It's not needed to complete the search. So in this case, if I think that I'm looking for damp Lyman alpha systems, or I want to know everything, then you might think, oh, well, why don't you just look for just a couple of different pairs of transitions because of the strongest ones, for example, magnesium-2. Well, obviously, magnesium-2 is only detectable over a certain range of redshifts, whereas these much bluer lines, the silicon-2 1526 line, here we go, silicon-2 1526 and the iron 1608, much bluer transitions, so you'll find much higher redshift systems, possibly damp Lyman alpha systems where these two things are nice and strong. Also, remember that there can be gaps in the spectrum, and so it's possible that you've missed at some absorption redshifts one or both of these transitions. So it depends on how thorough you want to be as to how much you want to search. In this case, let's just see if we find anything here. I'm not going to select that as something, otherwise we probably see something there, and we've already seen that this is probably a carbon-4 absorber. Is that something? Probably not. You can't be sure, of course, we're only looking at two velocity structures here, but this is probably something here where we see, of course, the iron 1608 line is a bit weaker, the silicon-2 1526 is fairly strong. We can select that as an absorption redshift. This is unlikely to be real, firstly because I remember seeing this structure before, it was a silicon-4 absorber or something, but also usually the 1526 is much stronger than the 1608. Not orders of magnitude stronger, just substantially stronger. So I'm going to quickly zip through now, see if I find anything else that's interesting.
Redshift is up to 3.
Yep, so now our redshift is up to 3, so I'm just going to press quit. But now what you see is the next combination is including one of the same transitions, silicon 1526, but this time aluminium 1670. And so it's like a contingency, if you like, for having missed some absorbers where perhaps there was 1526, but the 1608 for some reason fell in a chip gap or was too weak, something like that. So I'm not going to actually do the search in this case, I'm just going to quit, but you can go through and search for that. Similarly here it's the iron 2 1608 and the aluminium 2 1670. So we've gone through 3 very common transitions in damp Lyman alpha systems at high redshift, trying to look for each of the pairs that are possible. So I'm just going to press no in this case. Carbon 2 and oxygen 1 are very, very strong lines, so they're good to search for, but they're not very different. They're getting very, very blue, so they're often in the Lyman alpha forest. If you're really serious about finding these two transitions, which can even be in quite weak systems, then you really ought to be looking in the Lyman alpha forest, and I'm not doing that here. So there's not much of a range in redshift that you can cover here before you exceed the redshift of the quasar. Okay, I'm not going to bother searching for that at length. The aluminium 3 doublet is a good one, firstly because it's a doublet, so it's easy to recognize, but it's sort of in the mid-ionization stage, so it's not a high ion or it's not a low ion. So sometimes you can pick out systems that you wouldn't otherwise find. It's also at a kind of a middling wavelength, 1854 and 1862. So it's not particularly high redshift or particularly low redshift like magnesium-2 probes. So maybe that's something. I might label it as such, just in case it is. Probably we'll find that same one in magnesium-2 because it was a pretty low redshift. Maybe that's something. It looks less likely though. The centroids of those features is not well aligned. This is obviously something. Although there may be a blend here or something going on because you see the relative strength of these two features is a bit mismatched.
And the whole blue side is very different.
Yeah, there's clearly similar features, but there's obviously something else going on here. So I'll just pick out this one as a redshift and just quit. Then there's a series of very weak lines that you might search for if you're looking for something in particular, or if you're just looking to pick out one particular absorption that you already know about based on a certain set of transitions, like zinc 2, chromium 2, nickel 2 are all very weak, but the magnesium 2 is very, very strong, and you should look for that all the time because you'll pick out even weak absorption systems here. The trouble is it's quite a red doublet, and so you're already starting at redshift. You're not going to extend to very high redshift in your spectrum. So starting at redshift 0.4, it's that strong carbon-4 system. I'd say in a typical line of sight, you're going to pick up, of all strengths, you're probably going to pick up 3 or 4 at least magnesium-2 absorbers. There's one. So you'll probably find that there aren't many other transitions, although at this redshift that we're going to detect, except I think this is the same redshift as that aluminium-3 system we picked out. So even the strongest ion lines you may not see in that absorption system. Obviously this is a whopping great one. I don't know where to select my redshift here. I'm just going to do it somewhere in the middle. Worry about the redshift later. These are all sky absorption lines, so you start to get a lot of false positives in these regions of the spectrum where you're just looking for doublets. That is closely spaced pairs of lines. You can see all the very weak sky lines we're picking up. But because we're looking for a fairly red pair of lines, it's probably important. We're still going to pick up plenty of absorption systems even in the red part of the spectrum. This is obviously one. Another one. I'd say that's pretty typical so far, although this is starting to look like a fairly rich line of sight. We'll see. And I'm just going to stop there because I'm getting a bit bored. Okay, so now you may not have picked up everything with this red doublet. It's nice and strong, magnesium-2, but you may not have picked up everything. So there's a couple of ion, well, I'm calling them pairs here rather than doublets. They're not strictly fine structure doublets. This is like the bluest of the bluest 2 of the strongest 5 ion lines in the red. And so you're going to be looking for effectively like a doublet, nice and close together, same velocity structure. In this case, the 2344 line is much stronger than the 2374, but again, not orders of magnitude stronger. There's the difference there. There's an absorption system, but considerably weaker than the corresponding magnesium-2. So I'm just going to stop after that one. Similarly, here are the 2 strongest iron 2 lines, although they're not very closely spaced. They're selected in this case on the basis of being the strongest 2 ion lines. And of course you start to notice that you're only going to pick up the same absorption systems that you've already identified elsewhere, but it's possible you pick up something different if for some reason you've missed the magnesium-2 doublets or something like that. And again, I'm just going to stop after selecting that one. Calcium 2 doublets, you find those in our, well, at low redshift in our galaxy. You can see here at redshift, we're at redshift 0. Whether or not there's actually absorption there, I don't know. I don't think so. Normally you'd find absorption around here from our galaxy, but it doesn't seem that we do this time. So I'm not going to bother looking any further, but calcium 2 is generally pretty weak. Titanium's interesting, but usually weak, like zinc and chromium. There's a bunch of different ones. Sodium 1, there's our own galaxy, plus sky emission. Here's some very narrow absorption from our own galaxy, or something.
Do you select that, or do you just go
I select it as a redshift, yeah, just so that then I can look to see what else we find at 0 redshift. The aim, of course, for many instances is to know what is blending with the higher, the absorption lines from the higher redshift systems that you actually want to fit in detail. But I'm not going to look much further than that. Okay, so it's finished its list of pairs of lines to look for.